Before we visit the distant planets, let's begin where it all started, with the blazing heart of our solar system, the Sun. The Sun is not just a bright light in our sky. It's a massive nuclear powerhouse. At the center of our solar system, it accounts for 99.8% of all mass. Yes, nearly everything in the solar system is pulled in by its immense gravity. It's a G-type main sequence star, or G-dwarf, and it's about 4.6 billion years old. Made mostly of hydrogen and helium, it burns at temperatures of over 15 million degrees Celsius in its core. To put its size into perspective, you could fit 1.3 million Earths inside the Sun. Its diameter is about 1.4 million kilometers, 109 times wider than Earth. The Sun has 6 main layers: the core, radiative zone, convective zone, photosphere, chromosphere, and corona. The energy we see starts deep in the core. Here, nuclear fusion occurs, where hydrogen atoms are fused into helium under extreme pressure and heat. This process releases incredible amounts of energy that takes thousands of years to travel from the core to the surface. After the core, energy passes through the radiative and convective zones, eventually reaching the photosphere, the visible surface of the Sun. Above that, the chromosphere and corona form the Sun's atmosphere, visible during solar eclipses as a glowing halo. The Sun does more than shine. It shapes everything in our solar system. Its gravity keeps the planets in orbit, but it's also constantly sending out a stream of charged particles known as the solar wind. This wind forms the heliosphere, a protective bubble around the solar system. When the solar wind hits a planet with a magnetic field, like Earth, it creates spectacular displays, auroras, near the poles. But the Sun's activity can also disrupt satellites, power grids, and communications on Earth. Every 11 years, the Sun goes through a solar cycle, switching magnetic polarity. This cycle brings sunspots, flares, and coronal mass ejections, all of which can impact us here on Earth. One of the Sun's most fascinating and dangerous traits is its magnetic field. This invisible force is constantly shifting and twisting, driven by turbulent motions inside the Sun. Sunspots are dark, cooler areas on the surface caused by intense magnetic activity. These spots are often the source of solar flares and coronal mass ejections, violent bursts of energy that can disrupt space weather around Earth. Scientists still don't fully understand how the Sun's magnetic field flips every 11 years, reversing polarity in a process that affects the entire solar system. What we do know, these magnetic changes can have very real consequences, even from 93 million miles away. What if I told you the Sun makes sound, not in the way we hear on Earth, but through vibrations and waves that ripple across its surface? NASA scientists have turned these vibrations into audible sounds, using data from instruments like the Solar and Heliospheric Observatory. It's called helioseismology, and it's like listening to a musical instrument the size of a star. These vibrations help scientists map what's going on inside the Sun, offering clues to its inner structure, dynamics, and even how energy moves through it. Now let's talk about one of the Sun's greatest mysteries, the solar corona. That faint, glowing crown you see during a total solar eclipse? That's it. Strangely, the corona is far hotter than the Sun's surface, reaching temperatures over 1 million degrees Celsius. Scientists still don't fully understand why. It's one of the biggest puzzles in solar physics. The corona is also the birthplace of solar wind and the origin of some of the most powerful eruptions in our star's atmosphere. The sun's power stretches far beyond space. It touches everything on Earth. Its light fuels plants. Its warmth stabilizes climates, and its rhythm gives our planet day and night. But this influence isn't limited to beauty or biology. It's a driving force of weather, oceans, and even technology. Every sunrise is a reminder that our star is more than a light in the sky. It's a lifeline. Without the sun, Earth would be a frozen rock drifting through space. It powers photosynthesis, the process by which plants make food, and oxygen. It drives our weather, warms the oceans, and gives us the cycles of day and night. Even our bodies are synced to the sun through the circadian rhythm. Our internal clock. Every second, the sun delivers more energy to Earth than humans use in an entire year. Think about that. Our connection to the sun isn't just scientific. It's deeply cultural and ancient. For thousands of years, civilizations worshiped the sun as a god, built monuments to track its movement, and relied on its patterns for agriculture and survival. From the pyramids of Egypt to Stonehenge in England, and the Aztec sunstone in Mexico, the sun guided everything from religion to timekeeping. It was revered as a source of life, power, and order in the universe. Even today, solar traditions and festivals, like solstices, remind us how central the sun has always been to human history. The sun is currently in its middle age, stable and burning hydrogen. But in about 5 billion years, the hydrogen will run out. When that happens, the sun will swell into a red giant, engulfing Mercury, Venus, and maybe even Earth. Its outer layers will drift away, forming a beautiful planetary nebula, leaving behind a dense white dwarf, a fading ember of what was once our life-giving star. This white dwarf won't be very dramatic, but it will mark the final stage of a star like ours. It will slowly cool and fade over trillions of years, a quiet end to a long and influential existence. But before that distant future, we have billions of years of sunlight ahead. Enough time to learn, explore, and harness its energy more wisely. It also gives us perspective. Stars are born, they live, and they die. Their lives shape the cosmos. Without stars like the sun, the elements that make up Earth and us wouldn't even exist. In its death, the sun will seed the galaxy with heavier elements, the very building blocks of new stars, planets, and perhaps life. So, in a cosmic sense, the sun's end isn't the end at all. It's a continuation, a transformation. It reminds us that even the mightiest things in the universe change, evolve, and pass on their legacy. And that legacy is us. But it's not just the end of the sun that makes it so significant. The entire process of a star's death, its final act of stellar evolution, has a profound impact on the cosmos. As the sun sheds its outer layers, it will release tremendous amounts of energy and matter into space, creating the raw materials for new celestial bodies to form. This is how the universe regenerates, through the death of stars. Stars like the sun are responsible for producing the elements essential to life: carbon, oxygen, nitrogen, elements that we are made of. These elements are forged in the core of the star, and when the star dies, they are scattered throughout the galaxy. These building blocks of life will then be used to create new solar systems, planets, and potentially new forms of life. As the sun evolves into its red giant phase, it will also influence the entire solar system in dramatic ways. Earth, if it's not consumed by the expanding sun, will experience extreme changes. Temperatures will soar, the oceans will boil, and the atmosphere will become inhospitable. Life, as we know it, will be extinguished long before the sun finally fades into its white dwarf stage. The sun's story is far from over. Now it's time to move forward in our journey. Next, we're traveling to Mercury, the closest world to the sun. Don't miss out. Hit that subscribe button and join us as we explore Mercury and beyond. Thanks for watching. And remember, the sun is only the beginning.